step to the next talk. It is given by Enrique Delgado, who is at present assistant professor at the University of Córdoba since the late 2020, his Department of Computing and Numerical Analysis. He defended his PhD thesis in 2018 at the University of Seville on the topic of numerical analysis of reduced order modeling for LES models. Later, he's been a postdoc in CISA, associated to an industrial project coordinated by Gianluigi Rozza, working for the company Biormoli Pharma. And his talk will deal with reduced base approximation for LES models. Thank you, Enrique.
Thank you, Tomás, for the presentation, and thank you, the organizer, for giving me the opportunity of giving this talk. What I'm going to talk is a part of my PhD thesis, that it was also in collaboration with Gianluigi Rozza from CISA. Okay, so the work that we want to perform is that the study of the air inside of a courtyard. We first start simplifying this this problem, just taking the cavity in which one of the vertical wall is heated with respect to the another one. Due to this effect, to this setting, the air starts to moving around the cavity from the coolest part to the hottest part. We want to perform a reduced basis formulation for this problem because this problem may depend on several parameters. It may be for physical parameters like the Rayleigh number, or just physical geometrical parameters like the height of the cavity, in this case, the height of the courtyard of the building. So I'm going quickly with the continuous with the equation of the problem. We consider the Navier-Stokes equation plus a Boussinesq approximation for the temperature. And we also consider the Smagorinsky approximation for the turbulent part. Here we consider the nonlinear term associated with the Smagorinsky term. And also we consider this term for the this nonlinear term for the temperature. So we perform a BMS Smagorinsky model in the same way that Samuele has explained in his talk. We decouple the velocity, temperature, and pressure spaces into the large resolve scales and the small resolve scales. And we consider that the velocity, pressure, and temperature are decomposed by this way. And we consider the less closure model, the less closure terms, as this one, where we are filtering here the velocity and the temperature. Okay, so note that all these terms are highly nonlinear, and I'm going to explain later on, but we have to treat it in a specific way in order to perform the reduced basis framework. So we define the high fidelity problem. In general, we will solve it by finite element, but we perform it in a general way. So performing a affine decomposition for the bilinear form, we deal with these operators that are linear or trilinear and affine with respect to the parameter. Right now, we are considering the parameter, the Rayleigh number, I forgot it. And here we also consider some nonlinear term associated with the BMS Smagorinsky terms that are highly nonlinear. So we perform a greedy algorithm in order to set the reduced basis. So in the first stage of the greedy algorithm, we take a random parameter of the value of the parameter. We compute the snapshot associated to this parameter value, and we also had to compute an inner pressure supervisor in order to stabilize the velocity space. So when we construct the first reduced basis spaces, we have here the pressure space, just the snapshot of the first pressure for the first parameter value. We have the velocity space that it's it's composed by the snapshot for the velocity and also the inner pressure supervisor associated to the pressure snapshot, and finally the temperature snapshot. So suppose that we have construct and reduced basis space of dimension n, from n to 1 to n max, and we need to enrich or reduce spaces. So first of all, we need to compute the solution of the reduced basis problem associated for these reduced basis spaces. And we will choose the next parameter value as the maximum of the error between the high fidelity solution and the reduced basis solution just computed here. And since this evaluation of the error might be very, very expensive computationally, we substitute it by a posteriori error bound that we will define later on. And once we have choose this parameter value, we enrich or reduce spaces, the velocity we enrich with the velocity snapshot and the inner pressure supervisor, and the velocity and temperature spaces, we enrich them with the snapshots. The consideration of the inner pressure supervisor is needed due to the stabilization, to fulfill the insub stability constant for the velocity and pressure space, reduced space, okay, in the reduced order level. But let's back to the computation of the reduced basis solution. Let's note that we have these operators that are linear and non-linear, and we can store it in the offline phase. So these matrices will be perfectly stored offline, but we have these non-linear terms that are related to the eddy diffusivity for the velocity and the temperature term. So what we have to do in order to treat this non-linear term, we deal with the empirical interpolation method that help us in some way to linearize these terms in some way. So thanks to that, we can approximate this non-linear term by sum of linear combination of some coefficients that depends on the parameter value and some functions that are totally independent from the parameter value. So by this way, we can approximate, for example, this term, this VMS-Makorinsky term, by this one, where here are totally parameter independent, okay? So we construct all these functions, Qj, offline, and the sigma j's just are computed just online as the solution of this linear system in each iteration. So I resume here the full system, algebraical system. Here, the matrix that we have to consider is the ones related to the linear and nonlinear term, plus the one that we have linearized thanks to the empirical interpolation method. So thanks to that, thanks to the empirical interpolation method, we are able to store offline all the matrices that appears here, and just compute online the solution, just changing the value of the parameter. In order to define or construct the a posteriori estimator, we deal with the Bressy-Rapat-Rabiar theory for nonlinear problems. For that, we consider and standardize one seminar for the velocity temperature. But the first issue that we find out is that the thermal eddy diffusion term is no longer Lipschitz, that it's a condition that is necessary in order to define and prove the existence of the a posteriori bound estimator. So in order to deal with this issue, we consider some regularization of the thermal eddy diffusion, just introducing a modifier that help us in order to get the Lipschitzianity of this term. Thanks to that, we can prove that the derivative operator is continuous, also is insufstable, and finally we prove that is Lipschitz, that it's continuous Lipschitz. So thanks to that, we define these quantities. The epsilon n is the norm, is the dual norm of the residual. This tau n that depends on the Isuf constant of the derivative operator, the Lipschitz constant of the derivative operator, and the epsilon n, and we define the a posteriori error estimator just by this quantity, and this is given by this theorem. Just note that when tau n is larger than 1, this a posteriori bound does not exist due to this term, and we consider at the first stage of the greedy algorithm, where the tau is larger than 1, we consider the proper tau as a posteriori error bound. So let's go to the numerical result for this part of the talk. This is the problem we are considering. This is the heated cavity. We heat this cavity, and the flow goes around in a circle in the domain. We perform a first numerical test from medium high Rayleigh number from 10 to the power 5 to 10 to the power 6. We consider a Taylor-Hood finite elements for velocity, P2, P2 for velocity and temperature, and P1 for pressure. And we consider this regular mesh for the computational domain. So here I show you a snapshot of the velocity and the temperature. As you can see, the velocity is quite near to the vertical walls, while the center of the domain is quite with low velocity, and the temperature is more or less stratified in all the domain, all the center of the domain, and just a height with high gradients near to the vertical walls. So here I showed you the evolution of the a posteriori error bound estimator when we increase the number of reduced bases, the number of bases in the reduced spaces. As you can see, we need such much number of bases in order to get the tau lower than 1. So we need about 52 bases in order to get the tau lower than 1. And here I showed you what's the a posteriori error bound and the error when we get here 64 bases. So as you can see, as we expected, the error is below from the a posteriori error bound. So here I showed you some presume of the data. We need about 64,000 degree of freedom for the finite element, and 150 degree of freedom for the empirical interpolation method, and the reduced basis degree of freedom at 256. So we perform some tests in order to get the speed up of the problem. More or less, we are about 300 of a speed up in the computation between the high fidelity or the finite element solution and the online solution for the reduced basis problem, with a very, very low error, as you can see here. So let's go to the last part of the talk. We consider a new problem in which we consider also not only the Rayleigh number as the parameter, but also the height of the cavity as a parameter. So in order to treat this problem, we have to pass through the original domain that depend on the parameter into a reference domain that are parameter independent. We perform it by a change barrier formula in an easy way. And thanks to that, we define here our high fidelity problem, the variational formulation, and it's given by these operators. As you can see here, once we have treated the change variable formula for our operators, the geometrical parameter can be treated in a same way as the physical parameter, just a quantity that are pre-multiplied by the matrices. All these matrices can be stored offline, and all these matrices, these four matrices, can be linearized again by the empirical interpolation method in order to be able to store all these quantities offline and perform the online phase. Quickly, I'm going to explain the two different numerical tests. We consider first only the geometrical parameter, and then the geometrical and the physical parameter joints. We consider this computational domain, and these are some snapshots for some different values of the parameter of the geometrical parameter. As you can see, the velocity field is quite different, and we are not changing here the Rayleigh number, just changing the height of the aspect ratio of the cavity. Here I showed you a comparison of both problems. First, just taking the parameter value by this way, the height would be 0.5 to 2. And here is the same problem, but ranging the Rayleigh number between 10 to the power 3 and 10 to the power 4. So as you can see, we also need a quite high number of bases to get the source. Also, even more when we consider both parameters. Here I showed you the comparison of the a posteriori error bound for both problems, and here some the same resume for the speed up of the computation. When we consider only one parameter, as you can see, the speed up is more or less the same as before, about 300. But when we take a more complex problem and we consider both the physical and geometrical parameterization, the speed up it's quite low. It's about 50 orders of magnitude. So as conclusion, we have developed the reduced basis framework for the DMS Magorinsky model for natural convection problem. we have combined it into an empirical interpolation method 3D framework in order to linearize the nonlinear term. We have taken the modifier in order to regularize the non-Lipschitz term, and we have taken a good accuracy for the reduced basis solution with also big speed ups in the computation. And for future work, we are interested in increasing, of course, the Raleigh number. That leads us to non-stationary problems that the group of Thomas is working on. And finally, we are also working on take this VMS Smagorinsky model in the first stage without temperature, but considering wall laws in order to bridge turbulent flow. So nothing more. Thank you for your attention.
Thank you very much, Enrique. Are there any questions? Okay, Angelo?
Yes, I was wondering to what extent the model is robust to parameter variation, if it is somehow very sensible with respect to the variation of the parameters, or it spans a large variation of the range of the parameters.
Yes, it's very sensitive. Of course, all these parameter range may be very, very large. Of course, this when we consider both parameters, I think we can improve the results just taking short parameter range. So yes, and of course the sensitivity of with respect to the parameter is you can see it here when we need a lot of number of bases in order to get quite well approximation for the reduced basis framework.
And how does it depend on the sampling that you use?
On the sampling.
So in the sense, is it sensible to the sampling or?
Well, yeah, as you can see here, the solution is quite different. So the behavior of this flow is totally different from the behavior of this flow. Totally different. It's quite different. So yes, maybe the sampling takes this disadvantage, but in any case, I think we have a good how to say approximation. Even though we need to get a large number of reduced basis functions, so it's I think although this is quite complex, it's a good point to perform more complicated flows.
Thanks, Enrique. Very nice. Thanks.
Thank you.
Are there any other questions? Okay. Well, I just wanted to point out that the test cases that we are on screen are really academic. I mean, if the starting idea to perform this kind of computation was to optimize a courtyard. Courtyards are very used in Mediterranean climates to low temperature in summer, no? And I mean, for instance, the picture that we have on the right is not realistic. We will have, radiation just on the top of the courtyard and not on the full walls. Okay, and also the ratio, the aspect ratio, which is on the top left. I mean, you never will build a courtyard like that because you know it will be unuseful at all. Okay. Okay, so in practice, the shape is rather like the one on the right, and the variation of the parameters will be really in a small range. Okay, so for those, let's say, more realistic situations, very likely we will have better speed ups. That's very likely. Okay. Okay, so let me thank all the speakers. I know that the senior ones, because they are senior, and the young ones, because they are young, they are all very much busy, everyone in his own duty, and has been really a nice nice thing to accept to participate in this first workshop of the ARIA project. So really, let me deeply thank all of you. Okay, and I think we will have the occasion to continue discussing here and there. Thanks.